So where are semiconductors used? Some basic idea. Okay, I think not. Cool. So semiconductors are so before I'll come to that where semiconductors are used. But before let's take an example. So right here in front of you should be a simple circuit. There is a switch, there is a light bulb. Now what happens is when you press the switch, the bulb starts glowing, and you are able to see the current. You are able to experience the current going. Now, what does this has to do with semiconductors? Now, if you know, computers works in binary. So there is a zero and there is a one. That's how computers store memory. And to have zeros and ones, we need to have switches because zero is the absence of current and one is presence of current itself. So we need to have really small switches that are able to quickly perform zeros and ones because we want computers to be fast. So that's what we need, a switch. And what are the properties of that switch? We want that switch to be really small. We want it to be cheap and we want it to be fast. And that's what we're trying to do today. We're trying to make a switch that helps makes computer possible. A microscopic switch. Alright. So right here in front of you is a structure of how germanium exists in real life. So there is a germanium atom that is bonded with other germanium atoms. This doesn't have any free electrons with it. So it cannot conduct current. If there is sometimes randomly there is too much energy, one of the electron can randomly pop off and be part of the current, but it doesn't it isn't a good conductor, it's an insulator. Whereas compounds such as phosphorus, which have an extra atom, or aluminum, which has one less electron, they are good conductors. So how can we make an atom, a lattice like germanium, a good conductor? And that's what brings us to doping. Now, doping is, if you have heard about doping, so athletes use doping. They consume drugs. They consume performance enhancement drugs for to run faster or to be stronger. And that's what we're going to do. We are adding additional drugs to the germanium lattice to make it a better conductor. Now, one way to do that would be to add an atom such as phosphorus. So this phosphorus has a free electron. This free electron is just roaming around in the lattice, and that this electron will be the one that is going to carry the current. This is what we call an N-type semiconductor because this has an extra electron and electrons are negatively charged, and this makes the whole lattice negatively charged, and it's a negative N-type semiconductor. The other way to do that would be to add an atom that lacks an electron, such as aluminum. So it has three electrons in its outermost shell, and it's called a P-type semiconductor because there is it is positively charged. The lattice becomes positively charged. So an electron from outside can come in and fill this hole. And this is what we call the P-type semiconductor. By the way, if you want to explore this 3D model on your own, there is a lock symbol at the bottom right that you can click to explore these basically. Anyways, now how can we use this N-type semiconductor and P-type semiconductor to make a switch? I'll come to that, but before that, if we place an N-type semiconductor and a P-type semiconductor, one lacks an electron and one has an extra electron. What happens is the extra electron from the N-type semiconductor goes on and fills the hole in the P-type semiconductor. This is called a depletion layer. When an N-type and a P-type semiconductor are placed next to each other, some of the region in between gets depleted of its ions, gets depleted of the positive, the hole or the free electron that is present, and that is what is called the depletion layer. Now, one thing you need to know about depletion layer is that depletion layer is a poor insulator. Is a poor conductor. Sorry, it's a good insulator. So this right here solves the mystery of how we can make a switch. So if we can convert a semiconductor into a depletion layer, it will no longer conduct electricity. and it will be an off switch. If we can prevent this from happening, what's happening on your screen right now, free electron filling the holes. If you can prevent this from happening, then current can flow through these holes, and it will be a conductor. So this right here is a switch in front of you. All we need to do now is figure out a way to control this switch. That's what we're going to look at now. This is actually right in front of you should be a macroscopic structure of what we just saw. So this is the P region, this is the N region, this is the depletion layer. So current can flow through the N region, there are extra electrons. Current can flow through the P region, there are holes, but current cannot flow through the depletion layer. So this depletion layer right here is an off switch. Now, how can we increase or decrease the size of depletion layer? How we can create depletion layer, or how can we get rid of the depletion layer? And that is what we call controlling the switch. Now, if I add this is what we call biasing, forward biasing or reverse biasing. Right in front of you is an example of forward biasing. What happens is that we add a battery. We connect it parallel to this PN junction. It's called a PN junction because it's PNN, and junction means a combination of things. So when we pass current through this PN junction, these electrons go from P region to N region because this is getting more electrons and it doesn't need electron from N region anymore. So the electrons that were before filled with holes, the holes that are filled with the free electrons from P region, since this is negatively charged, these electrons are repelled back and they go back to the P region, and this leads to creation of holes on this atom. So this region again is now a good conductor, and this depletion layer is shortened. So if we were passing current through this region before, it was off switch, but now it is an on switch. This is what we call forward biasing, and this basically shortens the depletion layer. Now, how can we increase the size of the depletion layer? How we can have an off switch? So this is called reverse biasing, where we add a battery on the other side. Now we are sending electrons this way into the P region, and since this region becomes negatively charged, the electrons from the free electrons present in this P region are repelled. In the N region are repelled to the P region, which increases the size of depletion layer. So basically, here there was a free electron, but since this region is now negatively charged, it is repelled to this direction. It fills this hole. It increases the size of this depletion layer, and this depletion layer is now our off switch or a good insulator. And this is the you can use anything that has an extra electron instead of phosphorus. So any any element in the column of phosphorus. So if you open the periodic table, I'm sorry I don't have periodic table to show right now. Maybe I should have. So phosphorus lies below nitrogen, arsenic, antimony. So we can use arsenic instead of phosphorus as well. I don't think we can use nitrogen because it is unstable. Uh, can't put it in a compound and everything. But we can use arsenic or we can use antimony. So anything that is in the in the column of phosphorus. And similarly, instead of germanium, so if you look at the 3D model that we have, the microscopic 3D model, just let it load. Not this one. This one. So here we are using germanium, but instead of germanium, you can use silicon as well. I don't think you can use carbon because it is unstable. I think you can use carbon as well. I'm not really sure. In semiconductors, actually, a semiconductor with carbon is the best semiconductor because that is the semiconductor that is present in our brain. And if humans are able to do that, we'll be able to, you know, store as much information as we are storing in brain in the same size. So right now we need a lot of hard disks to store the information that is stored in brain. But if we can make a semiconductor with the help of carbon, it's going to get really, really cool. Similarly, instead of aluminum, you can use gallium or indium. What is the minimal size of depletion layer before quantum mechanical effects come into play? I think it was uh, somewhere around 20 nanometer. I'm not really sure. Uh, I can find that for you. Minimal size of depletion layer. It should be somewhere around 10 nanometer, somewhere around 10 nanometer, if I'm not mistaken. No, actually, no, no, I'm sorry. I think it should be even smaller than that.
Uh, Newton, one guy is not able to join the event, even though he's in the server. He's saying the channel is locked.
I think the person would have to complete verification before. There should be something in the rules. And we are really approaching. Is the minimum size connected to the atom thing? Yeah, it no, actually no. So minimal depletion layer depends on the size of the limitations of quantum mechanical effects. I don't think the size of atoms is concerned. I'm really sorry, I'm not that good with uh, quantum chemistry. I skipped that part. Uh, but I don't think the size of atoms come into the picture. It's about, since the size of electrons is consistent anyway and it depends on the distance between the electrons, the size of atom is not really concerned. Even if it is, it doesn't really matter. It's not significant either. Somebody correct me if I'm wrong. But that's, as far as I know, that's true. By the way, do you know the size of depletion layer that we have achieved so far? It is somewhere around 20 nanometers. So we have a switch, an electrical switch, that is the size of 20 nanometers. That's roughly the width of 10 atoms. So that's how small the switches are right now. And it's going to get smaller and smaller every year, every 2 years. Here is the answer to this. If you would, if you're interested, they're saying close to 5 to 7 nanometers. That's when uh, quantum mechanical effects come into picture. That's what Any more questions? Anyone? All right. If there are no more questions, uh, there is something that I would like you to do. Just a minute. Yeah. So I really wanted to take your feedback on how this lecture was. If there are any questions, keep them coming. I wanted to take your feedback on how this lecture was, and we used 3D to teach you basically, and how do you find it? Was it easy, convenient, or hard for you? And I would really appreciate if you guys can fill out this feedback. It will take less than 30 seconds for you to fill this feedback. Yeah, if you guys have any question, feel free to request for a speaker permission. I'll let you in. I'll prefer to talk to you rather than having chat messages for questions. We can have a two-way discussion.
Superior normal distribution. Maybe you want to sort of get into the VC and share your experience, how it was, where we can improve or anything. That is fine. You can be honest as honest as you want to be. Like that is what we really need.
Feel free to be honest.
Yep. Even feel free to be harsh. Basically, that is the name of us. Ogwe's real name is Harsh, so it in English says Harsh. Sorry, Harsh. Harsh. Right, Harsh?
Yeah. The form is not working. Give me just a second. Okay. So what was supposed to work is not working. That's make me concerned. Just a second. Uh, only. Can you reload? I think it should work now. You'll have to reload. I mean, can you confirm that the form is working for you?
Yep, it's working.
Um, the form is working. By the way, if you guys want something else, a lecture on something else, feel free to request. I'll be happy to take a lecture if it's okay with the admins. Just maybe DM me the topic if that, or send in the voice. I'll be happy to take a lecture on something that you want. A little about uh, us. I am the co-founder of a company that is trying to include 3D into education, and we want 3D to be a part, 3D and visualization to be a part of lectures itself, and that's what we're trying to do. This product that you just saw was super lectures, where basically 3D models and simulations and animations are I'm not a chemist by profession. I'm really sorry. Uh, I'm a student as well who's building this platform.
Yep. And down the line, we want to make it so gamified, you can say, that it becomes as fun as playing a video game, in the sense that you can pick up any electron, any atom, or any compound from the periodic table and try on if it is a good conductor or not. You can play with its electron with precise physics properties and all. You can sort of see at what deeper level it goes. Like you people were questioning uh, about the I don't know, the quantum, where does it break and all that, the quantum effect, how, what is the minimum size of the depletion layer before quantum mechanical effects come into play. So we want to make it the platform this way that you can sort of maybe decrease the size or anything to play and judge it yourself, how it will happen and where it will break and not. Yep, that's it from our side, I guess.
All right. That's pretty much it from my side. If you guys don't have any questions, we can end this. Pyridine, yeah, thank you. If that's all right, Pyridine, I think we can end the call.
Yep. All right, guys. Thank you so much.
Thank you for your time.